Mohan sir. Yes, let's start, ma'am. Shakti ma'am.
Sir, it's audible. Sir, start பண்ணிக்கலாம் sir.
Okay, thank you, sir.
Okay sir, thank you.
Thank you. So last class, no, previous classes, we have completed 3 modules. So in that modules, we have just completed the basic signals and systems introduction and continuous time signals and discrete time signals. The corresponding signals, standard signals representations, and there are some time scaling and time shifting, amplitude scaling. Those things have been discussed, right? With some practical examples we have just completed. So today we are going to discuss about the descriptions of systems. Okay. So here, whenever if we speak a particular system, it is nothing but no, like it responds when stimulated or excited, right? Whatever may be the system, like or circuit, like that has to stimulated or should be excited. That's what. So whenever if we speak about the systems, it is a system in any format, right, that has to respond when it is simulated or excited. I mean to say it has to subjected to some sort of input. So based on that, you will get some response. Okay. So the systems most commonly analyzed by means of engineers are artificial systems designed and built by humans. So thus engineering system analysis is the application of mathematical methods to the design and analysis of systems. So this is what we can able to define a particular system. And here there are some system examples like current, rate, thrust, and automobile chains. Like these are all some mechanical systems examples. Okay. And concept of feedback system. There is in a feedback system, the response of the particular system is feedback and combined with the excitation. So in such a way, it has to optimize the response in some desired sense. For example, if a particular system is feedback, there is the part of the output is taken and it has been given to the input, so that if any necessary corrections are to be incorporated in the output response, that has been done with the help of feedback systems. Like for example, temperature control in a house, water level control, pouring a glass of lemonade, as discussed in the previous classes, right? So these are some of the examples of systems. So whenever if I say system, that particular system requires some sort of input and output. So here the diagram, block diagram, represents single input, single output system. Okay, the system can be designated by H and the input is given by X of t. Okay, and output is Y of t. So that system, any system will have some inputs and outputs. Okay. So systems accept excitations, or sometimes we can call it as input signals at their inputs and produces the corresponding responses for the given excitations. Okay, in terms of output signals, or we can call it as response. Okay. So systems are often usefully represented by the block diagrams. So as I given, X of t is the input, single input, and it is subjected to a particular system and it has been given to the output section, that is your Y of t, that is the output response. Okay. And here multiple input, multiple output system block diagram. Okay, we can have the number of inputs. Okay, and for the corresponding inputs we can have outputs, whereas in the previous diagram, right, it is a single input, single output system. This diagram, multiple input, multiple output systems. So x1 of t and x2 of t is given in the systems x1, h2, h3, finally h4. So you will get the two outputs, y1 of t and y2 of t. y1 of t is directly taken from h1 of irresponse of the x1 of t, whereas h4 is the combination of h2 and h3 output. It has been given and finally it has been taken as y2 of t, right? So now here there are two inputs, x1 of t is applied to the h1 and x2 of t is applied to the h2 and h3. Okay, so this is the simple representative example for multiple input and multiple output system block diagram. And here the block diagram symbols, right? So 3 common block diagram symbols for an amplifier. So here that is your K stands for your amplifier, that is X is given and K is the multiplication factor. So finally you will get Kx. Okay. So we can have these symbols. So there are 3 common block diagram symbols for summing junction. See here, we can use this first. There are possible methods, but we can use this summer. Okay. So here X signal and Y signal is summed up, whereas X is plus and Y is minus. Therefore, finally you will get the output X minus Y. Right. So this plus symbol, or sometimes no summation symbol, and sometimes no plus and minus in this arrow mark, near this arrow mark we can represent. Right. These are all the common symbols. So in the problems, they may give any form. Right. That's what. And here the block diagram symbol for an integrator system. So for the integrator system, we can have the input signal X of t, right, and the corresponding output signal, and the system can be represented as a symbol integration symbol. Finally, you have the system output integral minus infinity to t x of tau d tau. Based on the time constant, the time signals will be integrated. So this is the block diagram symbol for an integrator. So you should know about the block diagram symbol for integrator and sum up, right, and these things for amplifier. For all these, you should know to design a system and as well as their realization. And here an electrical circuit viewed as a system. So here, so this is the diagram which is given, the electrical system. So low pass filter is given, resistor followed by capacitor, right? So here the input signal is given to the resistor with respect to the capacitor terminal V in of t. That is, your input signal is V in of t. Voltage is applied, right, with the polarity plus and minus. And I of t is nothing but the current flowing through the circuit. So whenever if you mention your signal and current, voltage signal and current signal in terms of t, it is for continuous time signals, right? Continuous time signal is applied to the system. So this is an simple electrical system, right, which consists of resistor and capacitor. It is an low pass filter, right? It is an RC low pass filter, and the circuit is excited by the input voltage V in of t, and for the corresponding V in of t, you will be getting the output response. So called output signal is V out of t, right? And I of t, current flowing through the resistor. So it can be viewed or can be modeled as a single input, single output system as specified in the first part of the slides, right? So there is a system, this is a single input, single output. Here the single input is V in of t and the output signal V out of t. So that with these signals I can able to model, that is, we can be viewed as a single input, single output system, right? Single input and single output. And here zero state response of an RC low pass filter, particularly for step excitation. Okay, so this is the time versus V out of t is given. So in an RC low pass filter, it is an initially uncharged capacitor, right, that can be excited by the step voltage. Suddenly we can connect to the resistor capacitor combination to the voltage. So that time, for example, if you are applying 5 volt, you cannot directly apply 5 volt, right? It reaches from 0 to 5 volt. Okay, so that's what the step response, step excitation, how the resistor and capacitor is acting upon it, right? That has been clearly given in this diagram. Okay, so for the particular step voltage of V in of t, right, AU of t, its response, that is the output response V out of t, is equal to, see here, A of 1 minus e power minus t by RC, right, into U of t. because it is subjected to step response. The moment if we switch on the circuit, okay, the voltage is applied to the RC combination. That's what. Okay. So this is a response called zero state response of this electrical system, because there was initially no energy stored in the system. I mean to say, in the capacitor it was initially not charged, uncharged capacitor. You just assume it is an uncharged capacitor. Okay. And because of uncharged, it was in its zero energy state. If the excitation is double, the zero state response also doubles, vice versa. Okay. And here for zero input response of an RC low pass filter. So here we need to concentrate on the zero input response of an RC low pass filter. See here, if an RC low pass filter has an initial charge on the capacitor, right? Okay. So it has some sort of charge in the initially in the capacitor of V0 volts, and no excitation is applied to the systems. It's zero input. That time, no, you will have the output response V out of t is equal to V0 into e power minus t by RC. Right? There may be some sort of zero input response of an RC low pass filter. That representation is clearly given in this diagram. Okay, it is a decaying exponential waveform. That's why it has given e power minus t by RC. RC is your the combination of resistor value and capacitor value. By multiplying, you will get the some factor that is a time constant which fixes the response. And here in the system you should know about the homogeneity. That is here in a particular system, if you want to say homogeneous, it has been multiplying the excitation by any means, like any constants, including complex constants can also be employed. So it multiplies the zero state response by the same constant. See here, the diagram is given for homogeneous system. X of t is input and y of t is output. Whereas here, in before to that homogeneous system, we have some multiplier, right? Here, x of t signal is multiplied with some value, so called k. So in the output of the multiplier, you will get kx of t. Now it has been given to the system H, which produces the output response, which is nothing but k y of t. And here, so we have to go for testing the homogeneity and homogeneous concept with the help of the logical process, right? So we need to apply a small signal g of t as the excitation signal x1 of t. So based on this excitation, we need to find the zero state response. That zero state response can be corresponding to y1 of t. Now we have to apply the signal kg of t as x2 of t, and we know that where k is a constant, that is in the previous diagram I have just known where k is a constant that has been multiplied with the x of t. So therefore we have to apply the signal kg of t as x2 of t for the finding zero state response. So now if y2 of t, that is nothing but ky1 of t, for any arbitrary values of g of t and k, then the particular system is homogeneous, right? So in short, we can say if g of t tends to y1 of t, kg of t also tends to ky1 of t, right? So whatever may be the signal you multiplied in the input, the same response will be applicable in the output response also. Okay, that's what. So therefore the system H is said to be homogeneous. So this has to be checked out for the number of system implementations. Okay, while going for the satellite systems and going for navigation systems, no, you need to know about the homogeneity. Okay, and these are all some of the example. See, let y of t is equal to exponential of x of t. So you need to find out, is the system homogeneous? So now x1 of t is equal to g of t, then y1 of t is also exponential of g of t, right? Now x2 of t is equal to kg of t, then y2 of t is equal to exponentials of kg of t. So now exponential of kg of t to the power k, that has been multiplied. So for this, we need to go for ky1 of t is equal to k exponentials of j of t, which leads y2 of t is not equal to ky1 of t. So therefore, the particular system is non-homogeneous, right? And similarly for this second example, y of t is equal to x of t plus 2, right? Then we need to determine the signal. So make it x1 of t as g of t, then y1 of t is equal to g of t plus 2. Similarly, x2 of t is equal to kg of t, then y2 of t is equal to kg of t plus 2. Now, if we combine to know the concept of homogeneity, ky1 of t is equal to kg of t plus 2k, whereas this y2 of t is not equal to k1 of t. So, for the given two system of equations are not homogeneous. Likewise, we can conclude. Okay, and if the system is considered, we need to know about whether the system is time invariant or time invariant, okay, based on the amount of delay, right? So I can clearly understand with this concept, if a particular system is excited by zero state response and we need to delay the excitation, simply it delays the zero state response, right, by the same amount of time. So regardless of the amount of delay, we can able to conclude the system is time invariant. Okay, so that has been clearly discussed in the following example. Time variant system is given and it is subjected to the signal x of t and which corresponds the output signal y of t. So now I am just introducing some time delay t naught. Okay, the x of t signal is applied with some time delay t naught. Therefore, this original x of t signal is to be termed x of t minus t naught. Okay, so obviously the output response produces some output with relevant to the delayed input response. So you will get y of t minus t naught. Okay, now if g of t tends to y1 of t, g of t minus t naught tends to y1 of t minus t naught. Okay, then the time is the particular system h is time invariant. Okay, time invariant in sense what? Whatever may be the delay, you make it in the input side, the same time factor delay is to be applicable in the output also. If that particular system obeys this, then this particular system is time invariant. Okay, and even if you introduce some delay, the output will be in the previous case, no, then the particular system will not be time invariant. It has been say that time variant. Okay, that's what. And some example, say y of t is equal to, again I am just giving the example, exponentials of x of t. So we need to find the system is time invariant. So we need to determine x1 of t is equal to g of t, then y1 of t is equal to exponential of g of t. Okay, so you introduce some time delay t minus t naught, okay, in the input side, and the output side also exponential of g of t minus t naught. Now you see that y1 of t minus t naught, again it is a exponential of t minus t naught, which leads to y2 of t is nothing but y1 of t minus t naught. Whatever may be the delay introduced in the input system of this particular signals, you will be getting the same output, that is so called time invariant. Okay, you can able to follow, students, kindly respond. Roll number 27, roll number 804. Are you online, right? Okay, keeping that you don't have any doubts, I'm just continuing. Then additive property, that is system, whenever the system is described, we have to determine whether it is an additive system or not. Okay, so if one excitation causes a zero state response with respect to the particular excitation, it will cause another zero state response, right? And if for any arbitrary excitation, the sum of the two excitations causes a zero state response, right? So that is the sum of the two zero state responses. Then the system is said to be additive. See here, there are two examples are given for knowing the concept of additive system. X1 of t subjected to y1 of t through the system H, x2 of t subjected to the system H, and the output response y2 of t. Now we need to add x1 of t and x2 of t with the help of an adder. Now you will be getting the output of the adder is x1 of t plus x2 of t, which is given to the one particular system H. Finally you will get y1 of t plus y2 of t. Okay, so this can be explained with the help of equations. If g of t tends to y1 of t and h of t tends to y2 of t, you add g of t and h of t, okay, with respect to the producing the system y1 of t plus y2 of t. So therefore the particular system H is additive in nature. Okay, so we need to determine whether the system is additive in nature or not, okay, based on this concept. Some examples, additivity, that is to know the concepts, no, we can have some examples. So let y of t is equal to u of x of t. So we need to determine whether this particular system is additive. What will you do? You make it x1 of t as g of t and y1 of t is ug of t. Similarly, x2 of t is h of t, then y2 of t is u of h of t. Okay, so let x3 be g of t plus h of t, then y3 become u of g of t plus h of t. Now you just add y1 of t plus y2 of t, so you will get ug of t plus uh of t, so which is not equal to ug of t plus h of t. Okay, because if you see that the arguments, it is not correct. Okay, so therefore it is not additive. For example, at time t is equal to 3, you just replace t by 3, you will be getting g of 3 is 4 and h of 3 is equal to 2. Whereas now y1 of 3 plus y2 of 3 is equal to u of 4 plus u of 2, which is nothing but 1 plus 1 is equal to 2. But for y3 of 3, it will become 1. 4 plus 6, 1. So for any values, no, it has to be additive in nature. But if the value is increased, for that purpose, I am just putting the third equation, x3 of t. Right? In the previous examples, only we have just made x1 of t and x2 of t. Right? We need to check one more input value. Right? So by checking this value, now you can able to find out this particular system is not additive in nature. Okay. And here next is linearity and Lte systems. So now we need to check, so far homogeneity and that additive property has been discussed, and linearity and Lte systems, that is we need to check whether the system is linear and thereby linear time invariant systems. So if a system is both homogeneous and additive, it is linear. That is we just discussed now the two properties, homogeneous and additive properties. If the system obeys this homogeneous and additive, then we can say that the particular system is linear. Now if a system is both linear and time invariant, it is called an LTI system, linear time invariant system. Okay, some systems now which are non-linear can be accurately approximated for the analytical purpose by means of linear system for small excitations. Okay, so now to depict the concept of linearity as well as linear time invariant system, consider any LTI system. The analysis of the effect of an excitation, what we have just applied to the particular system, we can found by breaking the excitation into pieces, that is by means of finding the responses to those pieces individually. Then we need to add those responses. See here, let x of t is the rectangular of t by 4. Now I can break x of t into u of t plus 2 minus u of t minus 2, or we could break into 0.75 rectangular of t by 4 plus 0.25 rectangular of t by 4. Okay, I'm just giving, for example, u of t plus 2 minus u of t minus 2 will give the same value. That's why even given after breaking, it gives the same value. So thus we need to make it as a pieces or into any other convenient form, that particular sum of functions that equals the x of t. Okay, and next concept is your stability. So whenever a particular system is said to be stable for all types of inputs, no, it has to be produced stable outputs. So bounded input and bounded output stable system, we can call it as BIBO system. For any system for which the response is bounded for any arbitrary bounded excitation, then we can say that particular system is BIBO, that is bounded input and bounded output system. So now see, a continuous time LTI system described by the differential equation is very stable if the eigenvalues of the solutions of the equation for all should have the negative real parts, right? In the equations, if we determine the imaginary and real parts, the equation should have the negative real parts. Okay, and causality, that is any system for which the zero state response occurs only during or after the time in which the excitation is applied is a causal system. Okay, we need to determine causal or non-causal systems sometimes, right? So by strictly speaking, all real physical systems are causal systems. Real physical systems can be termed as causal systems because here for any type of zero state response occurs during or after the time in which the excitation is applied. So that has been incorporated in the real physical systems. So therefore we can conclude that all the real physical systems may be causal systems. And memory system or memoryless system. Okay, you all know that. So whenever if a particular system will have the ability of storing something, it has been memory system. It is not, no, then we can have this system. So if a system zero state response at any arbitrary time depends only on the excitation at the same time and not on the excitation or response at any other time, it is called static system and is said to have no memory, right? So all static systems are causal. A system whose zero state response at some arbitrary time depends on anything other than the excitation, right? Same times it is called a dynamic system and it is said to be have memory. So any system containing an integrator has memory. With this concept, we can just conclude all static systems are causal systems, and if the system contains integrator, we can say that it is a dynamic system. That is, it has memory. Static non-linearity. So many real systems are non-linear because the relationship between the input and output, so-called voltage and current, between the excitations of amplitude and response amplitude is non-linear. So here for a diode, I've just given the voltage current relationship, VI diagram for linear resistor and VI diagram for diode is mentioned. So for the resistor, if you keep on increase the voltage value, the current will be keep on increased. Okay, if you determine the slope, it has been 1 by R. But if you see that VI diagram for a diode, after some particular values of voltage, no, the current is keep on increasing. That's what this is the VI diagram for a diode. And here static non-linearity you need to determine for an analog multiplier. The diagram analog multiplier is given. See here x1 of t and x2 of t, it is an analog multiplier. If the two excitations, see x1 of t and x2 of t, right, are the same signal, excitation signal, then the response signal is the square of the single excitation signal, and doubling the excitation would cause the response, to increase by a factor of 4, right? Provided if both the signals are same single excitation signal, right? Then such a system is not homogeneous and therefore not linear also. So here this is square. The same signal is just given multiplied and it will be given to the y of t is equal to x square of t. Okay. So this for an analog multiplier, if the two excitations are same single excitation signal, but the response signal is the square, that single excitation signal, and doubling excitation would cause the response to increase by a factor of 4. Okay, that's what we can conclude in this slide. And invertibility. Okay, invertibility in sense now we need to inverse the signal, that is the output signal can be given to the input. Likewise, my system is said to be invertible if unique excitations produces unique zero state responses. Okay, for example, we can say if a system is invertible, knowledge of the zero state response is sufficient to determine the excitation. See here, this full wave rectifier is given here. This full wave rectifier is a non-invertible system because now here the unique excitations produces unique zero state responses, right? Okay, so here particular system is invertible, then the knowledge of zero state response is sufficient to determine the excitation. But here in the given example full wave rectifier, it is not possible. Therefore this full wave rectifier is non-invertible system always. And dynamics of second order systems. See, these are the equations and very important for second order systems. That is, we need to go for calculating the eigen function of a linear time invariant system, which is a complex exponential form. So the eigenvalues of the second order systems are either real as well as in complex conjugate pair can be represented. Okay, so the general solution is the sum of two complex exponential along with the constant. The example is given, the capacitor voltage in a series RLC circuit excited by the voltage step of a height A, so called amplitude. So V out can be given as K1 e power minus alpha plus root of alpha square minus omega n square t plus K2 e to the power of minus alpha minus root of a square minus omega n square t. Then plus A. This A is nothing but your step height. So here in both the cases alpha can be defined as R by 2L in the first case, in second omega n square 1 by LC. Alpha is the damping factor and omega n is the natural radian frequency. And dynamics of second order systems, right? We need to introduce some critical radian frequency. Okay, that eta, this eta is equal to alpha by omega n, which is the damping ratio. With the damping ratio, we can able to get the critical radian frequency. Okay. And complex sinusoid excitation. Sometimes the sinusoids may be there is sine wave and as well as cosine wave, and in some cases complex sinusoidal representations may be used in the systems. So any linear time invariant system excited by the complex sinusoid which corresponds with the another complex sinusoid with the same frequency, right? So if you see that, we can the example is given for RLC circuit. See that the equation is given for the RLC circuit. B is equal to A divided by Z2 pi F0 square LC plus J2 pi F0 RC plus 1. That is in the case of RLC circuit, you consider the input voltage Vn of t is A e power J2 pi F0 t. Then the corresponding response, output response V out of t is equal to B into e power J2 pi F0 t. So here A and B are generally the notation of complex. That is, B can be found by substituting the solution from the differential equation form and finding the particular solution. So thus for RLC circuit you can able to go for the calculating the complex signals in this way. And for discrete time systems, so far we just discussed about the continuous time systems. Now we need to go for the discrete time systems. So with the increase in speed and decrease in the cost of digital system components, especially discrete time systems have experienced and are still experiencing, we can have some engineering systems has to be incorporated by means of digital aspects. So thus always your discrete time systems are described with the help of difference equations. Okay, see here the block diagram symbols for discrete time systems. So first we need to introduce the delay in the block diagram. The block called delay D, right? It is subjected to x of n and the output x of n minus 1. So this is the block diagram symbol for summing junction and an amplifier. Sometimes we can call it as amplifier, or the same for discrete time systems as they are for continuous time system. So this is your block diagram symbol. And here the discrete time systems, that is the events, the number of events occur at the different points in time. But we have to go for these points. The most important example is the digital computer, right? You all know. So significant events may be occurred at the end of each clock cycle and nothing of significance to the computer user. It has been happened between those points in time. So thus these can be clearly governed by means of difference equations, so-called discrete time systems, right? Let a discrete time system generate a excitation signal y of n, right? You understand n is the number of discrete time intervals that have been elapsed since some beginning time n is equal to 0. Then we can have the example of simple discrete time system governed by the equation. See the last I have given, y of n is equal to 1.97 y of n minus 1 minus y of n minus 2. Okay. So the equation says in words, I can say the signal value at any time n is 1.97 times the signal value at the previous time. N minus 1 is since can be clearly given by means of statement. The signal value at any time n is 1.97 times the signal value at the previous time n minus 1. Okay, minus the signal value at the time before that n minus 2. So if we know the signal value at any 2 times, we can compute its value at all other discrete times. This is very similar to the second order differential equation, in which we can have the 2 independent initial conditions can be allowed to find the solution for all the time, and the solution methods are very similar in these cases also. And here the discrete time system is described by the block diagram. We can solve this equation by the iteration with the help of the computer. The initial conditions, yn is equal to 1, yn1 is equal to 0, while 1, yn2 is equal to yn1, and similarly you can get yn is equal to 1.97 into yn1 minus yn2. Okay, that is for block diagram representation. I can give, you just take this y of n as your output, and from this you make the delay value, right? Y of n is subjected to 1 delay, you will get y of n minus 1. Now this signal is again subjected to another delay line. This one respect will be again delayed with another respect. Therefore y of n minus 2. Okay. So here this y of n minus 1 is multiplied with 1.97. So therefore you make the multiplier 1.97 in the output of the first delay element. So in this point you will be getting 1.97 y of n minus 1. So here the output of the second delay element y of n minus 2. So if both the signals are summed up here, so in this point, okay, you will be getting 1.97 y of n minus 1, okay, minus, see here it has been mentioned minus. So So therefore minus y of n minus 2, which gives the output y of n. So this is y of n 1.97 y of n minus 1 obtained from here, and minus y of n minus 2. Y of n minus 2 is the second delay element output, and it has been minus. Finally you will get the equation, right? So in this manner we can able to represent the equation by means of block diagram representation. And here with the initial conditions y1 of 1 is equal to 1 and y of 0 is equal to 0, the 0 input response of y of n can be in this manner. For 50 sequence, 50 number of sequences it has been given, and we need to go for the solving the difference equations. Okay, by means of iterations we have to solve with the help of constant coefficient of ordinary differential equations with the available techniques, and we need to find out the eigenfunction of this type of equation, right? And we have to take the homogeneous solution of this equation. So after taking the homogeneous solution, we need to substitute the value with the equation, then we can get the final characteristics equation. So after getting the characteristics equation, we can able to divide the constants. K is at power minus 1. So similarly you will get the corresponding particular solutions as z is equal to 1 by 2. So in this manner you can able to solve the difference equations. So that is the eigenvalue for the 2y of n minus y of n minus 1 is equal to 0, and then z is equal to 1 by 2 as per the homogeneous calculation we obtain, and we can substitute to get the total solution. Okay. So now we can have the eigenfunctions of LTI systems. So eigenfunction of any linear time invariant system is the complex exponential. Okay. So either it may be real or complex. It occurs in a complex conjugate pairs. Okay. So LTI systems can be excited by means of complex sinusoidal response with another complex sinusoid of the same frequency. Okay, but if you see that we can have a different amplitude and phase in general. Okay, so all these statements are true for both continuous time and as well as discrete time systems. Okay, so within this module, we completed the concept of systems, both continuous time systems and discrete time systems. I'm just recalling. You just kindly go through the slides from the beginning. I'm just recalling. So we can go for the next module, time domain system analysis. Okay. So with the previous modules, we have just given the concept and how to determine the various systems realizations along with the practical examples. Okay. With that, we can go for the analysis of system in terms of time domain. Okay. And first we'll start with the continuous time. So for continuous time systems, we can have the impulse response. Okay, so the system can be described by these equations: a2 y dash double dash of t plus a1 y dash of t plus a0 y of t is equal to x of t. So here, let the excitation be a unit impulse at any time t is equal to 0. Then the corresponding 0 state can be represented as in terms of impulse response. See, you just replace all y by h, right? In this equation, just you replace y by h. So thus, the impulse occurs at time t is equal to 0 and nothing has excited the system before that time. That is the meaning. So therefore, the impulse response before the time t is equal to 0. Especially this is for causal system, right? So after the time t is equal to 0, the impulse has occurred and gone by. So therefore, there is no longer a particular excitation, and the impulse response is the homogeneous solution for the differential equation that has been specified here in the impulse response. Okay. So here for all time t greater than 0, the excitation is 0. So there is the response is the homogeneous solution of the differential equation. But at time t is equal to 0, the excitation is an impulse. Okay, that's what. In general, it would be possible for the response to contain an impulse along with the derivatives of an impulse, because these all occur at a time t is equal to 0 and are 0 after that particular time. Okay, and for the different cases, the impulse response is given. And here we need to find the constant k, integrate of h dash of t plus 3h of t is equal to del of t over the infinitesimal between the 0 minus to 0 plus. Okay, for the negative and as well as positive values. So as per the formula, you can write, then we have to incorporate the initial conditions in h dash of t and h of t. Okay, then we can substitute the value of u of 0 plus and u of 0 minus. Both u of 0 plus is 1 and u of 0 minus, you all know that as per the unit signal it's 0. Okay, and finally you will get k plus 3k e power minus 3t by 3 after integrating this k e power minus 3t u of t dt. Okay, you will be getting k plus 3k of minus 1 by 3 minus of minus 1 by 3. That term, the second term, no, that will become 0. So therefore you will get 1. That is k is value is equal to 1. That is h of t is equal to e power minus 3t into u of t. This is the impulse response for the given example. These are all some other examples. So the system can be described by the equations. Then we can go for the homogeneous solution. Y h of t is equal to k e power minus 3t by 4. And that is the form of the impulse response, especially for the time greater than 0. Okay. This is another example. We have to integrate again over the same infinitesimal interval. Along with the 0 initial conditions, we have to incorporate. Finally, you make it one constant, and you have to apply the initial conditions to get the infinitesimal interval values. So you will get h of t is equal to minus 3 by 16 into e power minus 3t by 4 into u of t plus 1 by 4 del of t. And this is for impulse response. h of t is equal to minus 3 by 16 into e power minus 3t by 4 into u of t plus 1 by 4 del of t. The original differential equations is given by 4h dash of t plus 3h of t is equal to del dash of t. Then we can substitute the solutions, when finally we can get the equation del dash of t is equal to del dash of t. This man can go for the calculation of the impulse response. And now the convolution integral. If a continuous time linear time invariant system is excited by an arbitrary excitation, see here the exact excitation and approximate excitation is given. So for continuous time LTI system, the exact excitation along with the approximate excitation is given. So in both the cases, the response could be found approximately by approximating the excitation as a sequence of your continuous rectangular pulses with so-called with duration pulse with duration as TP. Okay, and approximating the excitation as a pulse train, we can be expressed mathematically. That is the approximation x of t, x of minus tp, rectangular of small t plus tp, that is the pulse width, plus x of 0, rectangular of t by tp, plus x of tp, rectangular of t minus tp by p. It goes. Okay, so finally we can approximate by summation of n varies from minus infinity to plus infinity, x of ntp, rectangular of t minus ntp by tp. Okay, so this the convolution integral can be written in the terms of pulse with tp along with the unit area. So in the second half, in the equation, the shifted unit area pulse has been represented. There is 1 divided by tp rectangular of t minus ntp by p. So this is the rectangular of tp period. For this period, we have just obtained the convolution integral. Okay, the same thing is mentioned here. For the unit impulse response, the excitation and the response become the exact value. Okay, so this is the representation of unit pulse. For the unit pulse response for the particular RC low pass filters. And here the x of t be the smooth waveform and let it be approximated by a sequence of rectangular pulses. Okay, in the dark line is exact and small line now that light dot line approximate value. And here the approximate excitation is the sum of rectangular pulses. See, there are a number of rectangular pulses as specified. It has been summed up here, and finally you will get the values, the waveform like this. And here the convolution integral for the approximate response is the sum of pulse responses for the various impulse response, h of t likewise, no? So all this will be summed up along with the pulse duration tp. Finally you will get the y of t value. Okay, see here for pulse duration of 0.1 second is mentioned for unit impulse response along with the unit pulse response. Okay, the exact as well as approximate value is given here in these diagrams, and this is for pulse duration of 0.05 seconds. Okay, and here superposition integral and convolution integral, there are two approaches. If that particular pulse duration approaches 0, the convolution integral expression may be used for approximate excitation, and as well as the particular response may be approached to the exact forms in both the cases, superposition integral along with the convolution integral. So this is a graphical illustration of the convolution integral. The convolution integral is defined by means of x of t convolution. Okay, this symbol is convolution, h of t, which gives the integral minus infinity to plus infinity x of tau h of t minus tau d tau. Okay, so here we need to illustrate the excitation x of t along with the impulse h of t. Okay, by being the two functions, see h of t and x of t. So this is the graphical illustration for h of t minus tau. That is the variation in time constant, and here it has been just transformed going from h of t to h of t minus tau. In the previous case it is minus 1, so in this case there is t to t minus 1. That is the difference here, and this is for t is equal to for 5. So you will get this value. And for y of 0 is equal to 2, the area under the product can be mentioned like this. That is the shaded part, no, is the x of tau h of minus 2 for the corresponding convolution integral at time t is equal to 0. And these are all the various process of convolutions for the illustration of the convolution integral for finding the y of t for different values of t, that is minus 1, minus 0.5, t is equal to 0, plus 0.5, 1, 1.52. For all these values we can able to get the graphical illustration of the convolution integral. This is the examples for t greater than 0 and t less than 0. Okay, for all time t, now we can get the values v out of t is equal to 1 minus e power minus t by rc u of t. So the previous examples are consolidated here as the convolution examples. Okay, and there are some properties in convolution integral. There is commutative property and associative property and distributive property. Okay, so in short, no, we can have x of t convolution y of t is equal to y of t convolution x of t. Okay, so this is the property of commutative. We can mutually commutate each other. Even if we have a commutation of a signal x of t and y of t, that will be equal. That's what. And we can associate the convolution integrals by means of, say, in this property x of t convolution y of t, both the signal is convoluted z of t, we can write x of t convolution of y of t convolution z of t. In this manner I can able to have the property, associative property. We can associate z of t along with the y of t. Similarly, we can distribute the signals. See, x of t plus y of t, the combination of these signals, if it is convoluted with z of t, we can distribute z of t as x of t convolution in z of t plus y of t convolution z of t. In this manner we can able to distribute these signals. And this is your unit triangle function. Triangle function, that is your t mod of t, that is in both either cases plus and minus, lies less than 1 is 1 minus t, and if it is greater than or equal to 1 it is 0. This is the unit triangle representation, which is the convolution of unit rectangle as specified. So now we can go for the system interconnections. Okay, we can have a cascade connections. Cascade, that is several systems can be connected together by means of some interconnections. If the output signal, if the output signal from a particular system is the input signal to a second system, then the systems are said to be cascade connected as specified here, right? So it follows from the associative property as specified in the associative property of convolution. That is the impulse response of cascade connection of linear time invariant systems. It is the convolution of the individual impulse response. Okay, and parallel connections, if the two systems are excited by the same signal and the corresponding responses are added, then they can said to be parallel connected. See here, in the previous case the two corresponding sequence connected in series form is cascade connection, whereas here in this case, see, if two systems, say h1 of t and h2 of t, right, are excited by the same signal x of t, and the corresponding responses are added with the help of sum. Right, finally you will get y of t is equal to x of t convolution h1 of t plus x of t convolution h2 of t. We can write x of t convolution h1 of t plus h2 of t. Okay, this is the parallel interconnection systems. So unit impulse response and unit step response. In any LTE systems, let an excitation x of t produces the response of y of t. Then we can go for the differentiation x of t will produce the response d by dt y of t. So we can follow that the unit impulse response h of t is always the first derivative of the unit step response. Okay. And stability and impulse response. A system is bounded in bounded output stable if its impulse response is absolutely integrable. That is, if integral minus infinity to plus infinity h of t dt is finite. Okay, then we can say the particular system is bounded input, bounded output stable. And the systems can be described by the differential equations. Okay, so the differential equations become an algebraic equations as specified here, and the transfer functions now can be called as rational functions because here the ratio of polynomials in terms of s. Therefore the transfer functions may be encapsulated for all the system characteristics, and we can have a great importance in the signals and system analysis, these types of differential equations. And this is the MATLAB system objects that is not required now. And here now it comes discrete time systems. The same, similarly for continuous time we can have the impulse response, but only thing is in terms of discrete time in nature. In terms of discrete the impulse response may be conventionally designated with the help of the signal h of n. So for both the cases h of n is equal to 0 for n less than 0. Okay, this is the example. Again the here for a particular system can be described by this equation, say 4y of n minus 3y of n minus 1 is equal to x of n. Then we can have the excitation as a unit impulse, that is 4h of n minus 3h of n minus 1 is equal to del of n. Again we have to go for the calculation of eigenfunction from the complex conjugates concept, right? So after obtaining, if we solve, you will get z is equal to 3 by 4. So therefore you can get the homogeneous solution in the form of h of n is equal to k of 3 by 4 power n. And the same example is given here. And this is for another example. So we have to go for the eigenfunction in the complex exponential form, and we need to substitute in terms of homogeneous differential equations, right? Finally you will get the solution in the form of k along with the k1 and k2 terms in terms of complex conjugate forms, both real and imaginary terms. See, this particular equation is represented in terms of graphical representation, h of n versus n, impulse response for the various number of sequences. Now we can go for system response. So now the response to a unit impulse is known, then we need to determine the response of the particular LTE systems in any arbitrary excitations that can be easily calculated. So now any arbitrary excitation, it is a sequence of amplitude scale and time shifted impulses. Based on this you can able to get the response of the system. So thus The response is simply a sequence of amplitude scaled as well as time shifted impulse responses. Based on this, you can able to get the system response. See here, these are all the simple system response example for system excitation, system impulse response, and system response for the corresponding values of number of sequences n. Okay. And the more complicated systems, in terms of system excitation, system impulse response, and system response can be overviewed here. Now, for discrete time system, we have to go for convolution sum, whereas in the previous case for continuous time, right, we have just discussed convolution integral, that is for continuous time. For discrete time, we need to calculate convolution sum. Okay, for any response y of n to an ordinary, that is in the differential equation we have solved. So here we need to determine the convolution sum in terms of impulse response. Okay, so thus if you see that y of n is equal to summation, that is whereas in the previous case integral varies from minus into plus infinity, but convolution summation varies from minus into plus infinity, x of m into h of n minus m. This is the convolution sum for discrete time system. The various examples for x of n and h of n, and h of minus m and h of n minus m. There is a delayed sequences. You can have the pictorial representations here for the various sequences of n between minus 4 to plus 4. This is for n minus 1, 0, and y of minus 1 is equal to 2 and y of 0 is equal to 6 for these values. And here also we can have some convolution sum properties. Okay, these are all the properties, like x of n convoluted with a del of n minus n, which becomes a x of n minus n naught. Okay, so there is the sum of the impulse strengths in y is the product of the sum of the impulse strengths in x. So similarly, the sum of the impulse strength in h can be the sum of the impulse strengths in x, right? That's what. So here again, commutative, associative, distributive property in terms of convolution sums calculated. Commutate, we can commutate like x of n convolution y of n can be commutated with y of n convolution x of n. Similarly, we can associate the signal z of n with y of n. Similarly, we can distribute the signal z of n with y of n and x of n. So that's what the property explains. The numerical convolution is in terms of MATLAB form. And here also for discrete time system, we need to know about stability and impulse response. It can be shown that a discrete time BIBO stable system has an impulse response that is absolutely summable. Okay, whereas in the previous case it was absolutely integrable, that is summation of minus infinity to plus infinity, h of n is finite. Okay, so then we can able to, if this particular equation is satisfied, we can say the given discrete time system is bounded in bounded output, stable. And here also we can have the cascade connection and parallel connections of distributed systems, right? If the systems are connected in series, two systems can be viewed in a single system whose impulse response is the convolution of the two individual system impulses, right, as per the property of associative. And again, it's a parallel connection. Here works with the property of distributive property. We can distribute the signals. That is, it is a single system whose impulse response is the sum of the two individual systems along with the impulse responses, right? and this is the unit impulse response and unit sequence response. So these are all the systems described by the differential equations. Okay, with the help of complex we can able to perform. We can write the differential for the discrete time system descriptions. Then we can obtain the transfer functions and we can transform with the differential equations for the discrete time systems. And frequency response of a discrete time system, that is x of n is equal to x e power j omega n. So you need to carry out the y of n is equal to y e power j omega n. Okay. So for delayed signal, x of n minus k and y of n minus k is given written, and the general difference equation, especially for this description pertaining to the discrete time system, can be written like this. That is y e power j omega n summation of k is equal to 0 to n a k e power minus j omega k. That can be x e power j omega n summation of k is equal to 0 to m. Okay. bk e power minus j omega k. With this now we can able to calculate the frequency response. So this the transfer function with replaced by e power j omega can be written like this. And this is the frequency response example. So let a system can be described by the differential equation, so called 8y of n plus 4y of n minus 1 plus y of n minus 2 is equal to x of n. So now we need to find out the response to the unit amplitude complex sinusoid at radian frequency. Then we have to graph the amplitude of the post complex sinusoidal response with the frequency, cyclic frequencies. Okay, so that is you need to know about, you have to replace by a j omega n, you need to determine the transfer function. So once if you write the transfer function, you can able to have the h of z. H of z is the transfer function 1 divided by 8 plus 4 is z power minus 1 plus z power minus 2 will be the transfer function. So here based on this you can able to calculate the frequency response and its symbol frequency response graphical representation, that is for from between minus 4 pi to plus 4 pi we can have the response, system response for the given transfer function. Okay, so now we'll have the revision of this system. You just go through the topics. If you have any doubts, you kindly clarify. Okay.